Good afternoon. Welcome to this month's member webinar hosted by Wisconsin Cheesemakers Association. I'm Grace Atherton, WCMA's Communications Director, and I'm so glad to have you all with us today as we dive into an evergreen topic in our industry, water quality management, specifically water reuse and recycling in dairy processing. Before we get things started, I want to share a couple of housekeeping notes. Please make sure your mic is muted and your video is turned off to avoid interruptions during our webinar. You can submit questions in the chat at any time during our session, and we'll do our best to address all of those during our Q&A with presenters at the end of today's webinar. And I wanted to let you know that a recording of today's webinar, along with a list of resources and contact information, will be shared with you later this week if you registered for this webinar, so please watch for that in your email inbox. I also want to thank our sponsors for today's webinar, Nelson Jameson and Applied Science. We appreciate your generous support. If you'd like to learn more about sponsoring a future WCMA webinar, please head to wischeesemakers.org/webinars or contact me for more information. And with that, I'll turn things over to WCMA's Executive Director, John Umhoefer, to review our agenda and get us started. John?
Thank you, Grace. Good afternoon, everyone. It's great to have you joining us for this discussion of water use, water reuse, water recovery, water recycling in dairy, and we have a great turnout. So I'm not going to slow us down. We've got great speakers. I'm going to walk you through the agenda very quickly. We're going to start out with Dean Sommer, cheese master, cheese technologist at Center for Dairy Research. He's going to talk about the new Dairy Wastewater Fundamentals short course coming up August 26th, really trying to get the whole industry to show up for that. It's going to be great. Then we're going to have Scott Fisher, the Director of Food and Beverage West Division from the Kurita Group, talk to us about cow and polished water use in dairy. Then we're going to have Aaron Shaver from Advanced Process Technologies. He's their Senior Technology Advisor. He's going to talk about water use in cheese plants. And Rachel Kloos with ISG, their water and wastewater group leader, is going to talk about water recovery from dairy processing wastewater. So great topics, good stuff. So I'm going to kick things right over to Dean Sommer to tell us about the new short course.
Thanks, John. So as John mentioned, we have a new dairy wastewater short course coming up. So I want to alert all the webinar participants today that the Center for Dairy Research, working with John and the Wisconsin Cheesemakers Association, will be conducting this one-day Dairy Wastewater Fundamentals short course on August 26th coming up. Registration for this course is now open. The speakers will be from two firms that have demonstrated excellence in dairy wastewater treatment, the Probst Group and McMahon & Associates. The location will be at McMahon Associates offices in Neenah, Wisconsin. Just real quickly, objectives. Remember, this is a fundamentals course. So objectives of wastewater treatment, terminology that's commonly used, differences between dairy waste treatment and municipal wastewater treatment, sources and attributes of dairy wastewater, regulatory limits and the permitting process, wastewater treatment options, and optimizing wastewater treatment operations. So again, the short course will be held at the McMahon offices in Neenah. It'll start in the morning. Registration at 8, the lectures at 8:30. We'll break around 1 o'clock and then travel over to the nearby AgriPure Little Chute new waste treatment system just on the north side of Appleton. So we've resurrected this course after it hasn't been offered for a few years. So we're hoping we get a really good turnout. And if this works out well, in the future, we hope to also offer an advanced dairy wastewater treatment course as well. Any questions, you can go to our Center for Dairy Research website. So with that, I'll end. Thank you.
All right, thank you, Dean. I note on the website that we are about half full already for that August 26th opportunity. We have 22 signed up so far. So best jump on it now or get your people in there to learn the fundamentals. I'm going to shift now and welcome Scott Fisher from the Kurita Group. And he's got his talk today on cow and polished water use in dairy plants. So take it away, Scott.
Great. Thanks, John. And thank you to Wisconsin Cheesemakers Association for allowing me to present on water reuse. I think what's helpful for the audience to know is that the way the presenters are going to present this material will be at a more high level with my presentation and basic concepts. We'll move into Aaron, who will get more into the details and distribution and how that works. And Rachel will then kind of bring it all together around best practices and how waste impacts from water reuse. So just want to give you that overview, and go ahead, Grace, and you can advance the slide. Just quick introduction. I'm Director of Food and Beverage. I've been a part of Wisconsin Cheesemakers Association for over 10 years. Been in water treatment for over 25. And interesting fact is my grandfather was a dairy farm inspector, so it's kind of in my blood to be a part of the dairy industry. And back in those days, people spoke as much German on farms as they did English. So that was the interesting comment he provided me. So you go ahead and move on to the next slide. You might wonder who Kurita is, just very high level. We deal with water treatment. So from water beginning to end, pre-treatment, utility water treatment, wastewater treatment, and then obviously we help support water reuse for our dairy customers. And that is why we're here today. So this is more of an example to talk about water reuse. You know, it was interesting hearing Dean and John talk about the topic of water reuse yesterday in one of our pre-discussions, because it's becoming more of a commonplace in the dairy industry in Wisconsin. Several years ago, it wasn't as common. And, you know, I think a perspective of where else on Earth and where else in the galaxy this happens. Kurita was involved with a water reuse application for the International Space Station over 10 years ago. And as you could imagine, you're taking urine and turning into drinking water. Why am I bringing this up during this conversation, you might ask, besides trying to gross you out? But the point being here is if mankind or humankind can take waste and turn into drinking water in outer space, I think we can collectively take fairly clean water in our dairy plants and make better use of it. So that's kind of my pep talk for this group and how we can do better with what we have in our facilities. So let's start as basic as possible. Obviously, I think we have a wide range of audience members here. We know milk comes into our cheese plants. Milk is 87% approximately water, and you know, solid materials are made from it, or semi-solid, cheese and whey powder. The waste from those processes is the water that's generated, and that's really why we're here today, is to say, okay, how do we take this material that's a waste from the milk that was the raw material and use it more effectively? So we'll get into that here. This illustration is pretty common for most people on this call. Really just highlights cheese production, you know, where raw milk goes through various processes, pasteurization, separation, you know, the key ingredients of microorganisms and rennet being added, and then voila, we have cheese curds that are then created in the process. I know there's it's a lot more complicated than that, but I'm really simplifying it. But then we also have liquid that's generated from this process in whey, and that liquid is the thing that can then be further refined for byproducts as well as water reuse. So you can kind of see it circled there in an illustration. So that's really more for others' benefit to say, okay, where are we talking about and what is the opportunity? You can advance, Grace. Okay, so I'm going to, again, simplify this statement around the whey production and a couple of different examples. Each plant is different. The complexity of these processes is different at every plant. So you'll just have to bear with my simplicity, but I think it's helpful to break it down into two different sources of concentration. So first example would be membrane. So we're taking the whey liquid, sending it through a process RO. The valuable piece would be the whey concentrate. So we're concentrating the whey solids. And then the permeate from that process is the waste. So that's the clean water that's generated from the RO. Now, what makes it complicated is some plants call that cow water, even though it's really not condensate. But regardless, it's the permeate water is the clean water that we're targeting as a water reuse. The second example is in evaporators, where whey liquid enters the evaporator. Steam drives the process to refine and concentrate the whey solids. And then we have a fairly pure water source that's generated. And that truly is cow water or condensate of whey. And that's really where the term comes from. Some questions might be, well, what process is better for water quality? I've seen both create exceptional water quality. It really comes down to maintenance. It comes to membrane life, how efficient is the evaporator, all those types of factors that are much more detailed than we're going to get into in this conversation. But do know that the water quality generated by these systems is very pure. So, based on the water that's generated, the Pasteurized Milk Ordinance, or PMO, in Appendix D of the 2023 document highlights the different categories of water. And you'll see them listed here. And if you'd like more details, you can dig into that in the document. But as you should know, Category 1 is the most clean water, meaning it's potably equivalent water source. It's I think it's the most stringent, and where you can say it's approved for almost every use outside of domestic water. So sink, drinking water, toilets. Otherwise, we can use it in most areas of the plant. Category 2 is less stringent, but you still can reuse it in many different locations within the plant. Category 3 would be a lesser quality water, but there's still a lot of uses in dairy plants where that water could be utilized. Again, we can dig into that more in detail in the Q&A or offline as far as how to validate or communicate around these qualities of water. Grace, if you'd like to go to the next slide. Category 1 water is water source that is, again, potably equivalent, and there are some requirements if your facility is trying to achieve Category 1 water that you should be aware of. It has to have a very low bacterial count. There's a fair amount of testing protocol that's required for that to be Category 1 water. So after approval from the state, you need to validate the operations for 2 weeks, and also know that if there is interruptions in the system, you need to revalidate the process for at least a week. Things like turbidity, connectivity would be measured, measuring and monitoring COD levels, as well as automatic dump systems so that you can purge water if it doesn't meet spec and you're not creating any quality issues. It's also good to note that any chemicals applied to this system need to be potably approved chemistries. Not everything can just be used in these applications. So that should be an important factor as you evaluate the whole opportunity for Category 1 reuse. Grace, you can go ahead and go to the next slide. So really high level, what is the benefits of water reuse? You're reducing the amount of water coming into the facility. If your wastewater facility is hydraulically loaded, you're also reducing the amount of wastewater sent to downstream. Rachel will talk more in detail about that later. And then sustainability improvement. I think not only from a environmental standpoint, this is beneficial, but we also see in the marketplace that the customer is very interested in sustainability and how are companies leading their industry in the way they handle water and various forms of sustainability aspects. So I think those are things from a brand standpoint that could set you apart from others in the marketplace as well. And then finally, this is something that Aaron's going to get into in greater detail: water quality and water quantity. You really need to understand the impurities that are in the water. And like I said, it's generally in good quality water for reuse, but you need to validate that. And then also have the supply and the infrastructure to utilize this water based on the peaks and valleys of production and CIPs and all the things that are associated to dairy plants. So that is the high level overview. I'll turn it back to John.
All right, that's a great place to start. Thank you very much, Scott. We will proceed right away to Aaron Shaver from Advanced Process Technologies. Aaron's going to take the ball from here. Thank you very much. And unmute at the same time.
As soon as I find my unmute button, I'll be good to go. Go ahead, Grace. So that's me, Aaron Shaver. I've been in this general type of work for about 30 years. I've been with APT for 15 of those years. And for those who might not be familiar, APT is based in Minnesota. We are an integrator that provides equipment, installation services, automation, engineering, and design to the cheese and dairy and beverage markets. And happy to have the opportunity to be here and talk to everybody today. Go ahead, Grace. Water is used in a lot of different ways in a cheese plant, and water quality affects all of them. Chemical and biological aspects of product contact water are critical to the product quality of what we're trying to make and the safety of that product long term. Similarly, mineral content that can vary in water chemistry can be a problem for CIP and can foul heat exchange equipment. So quality of water matters in a lot of different places in our cheese plants. And treatment of that water, even the fresh water coming in, is an important aspect of water quality in the cheese making processes. Go ahead, Grace. We have a lot of different types of water we talk about in cheese plants, and certainly we're focusing, I think, on cow and polished water a little bit today, but potable water and its source, whether that's well water or municipal water, and then treated water, which could be soft water, are also water types that are pretty critical to cheese plant operations. And I would say most operations today have at least 3, if not all of these types of waters present, depending on how they're operating. Soft water is traditionally made by either ion exchange, which is like a salt type system that you might have in your home, or reverse osmosis, which is going to generate a higher purity water and not require all that salt, because our friends in waste treatment, I'm sure Rachel would appreciate us not sending large volumes of brine at her through a traditional ion exchange system. So these are the different types of water that we see used, and certainly quality of all of these types of water is important to running a good cheese plant. But with that, we're going to tend to focus on cow and polished water. I will make one comment that traditionally, and at least as far as I'm referring to polished water in this process, we typically think of polished water as not just being water that's been recovered from an RO that's processing away, but that there's usually a secondary polisher, a second reverse osmosis system that's taking the water off of the product RO and polishing it again. And that second pass is really what's getting us to that very high level of purity. And so when I'm referring to polished water, that's really what I'm talking about in this conversation. Go ahead, Grace. So just how much water does a cheese plant use? Well, the answer is probably quite a bit. Typically, a cheese plant is running at least as much water in a day as it is milk. And that gets to be a fair bit. Certainly, as was mentioned by Scott, and unlike a fluid milk plant, the bulk of the water removed from the finished products of cheese and whey is the water that we want to target trying to reclaim. And in very efficient plants, which usually also means very simple and very large plants, it's not out of the question that those plants can operate almost 100% water neutral. In other words, all of the water they use for CIP and processing is coming out of the milk that they receive. There's a handful of things that doesn't work very well for, and you always have to have other water available so you can start up and run. But fundamentally, it's not out of the question for a plant to be capable of running very much on the water it's got coming in. I've kind of generated a little theoretical example that I'll kind of keep on a handful of these slides and talk about. But a theoretical plant consuming 3 million pounds of milk a day might consume 300,000 gallons a day of water in CIP solution and rinses for all the various processes it needs to run. It's going to have displacement of water for product and product flushes. Some of that water is going to go to the utility plants for steam, for tower water makeup and the blowdown of both of those processes. And then some of that water will be used for miscellaneous hygiene and sanitation in the facility. A lot of places water goes. Go ahead, Grace. So how do we keep track of where our water is going? We use what we call a water balance. And a water balance to us is really the accounting of where water is coming into and going out of a plant. So we want to look at all the different processes in that plant and what they are and what they're consuming. So the very basic version of that, without a lot of breakdown into pieces, is the product and product flushes, CIP rinses and solution makeup, and utility makeup that I had on this diagram. But to think about that a little bit further, then we say, where is that water coming from and where is that water going to? And as we look down a little further, we could say, well, maybe we're going to recover 250,000 gallons of that water from the whey. That's going to vastly impact how much we have to pump out of the ground or get from the city. And then where's that water going to land? Well, some of it's going to go out in product potentially. Some of it's going to be evaporated in the cooling towers. And if it's not one of those two, then we're probably sending it to Rachel in the waste treatment plant. So a water balance is really an accounting of where the water's coming to and going to and where it's coming from, so we can better understand what changes to our process might have both to our utility design and our overall system operation. Go ahead, next slide, Grace. So taking that a step further, we talk about what we think of as a scheduled water balance. The scheduled water balance is really that same list of things, but it's applying a production schedule over a 24-hour day or whatever suitable time frame makes sense. If your plant doesn't operate every day, maybe you want to look at it on a weekly basis. But certainly looking at an hourly basis is good in terms of identifying peaks and valleys in consumption. So this slide has a pretty simple little scheduled water balance on it, where we've got milk receiving showing up from about 4 a.m. until about 6 p.m. We've got standard cheese production, which would include pasteurization and vats and all the finishing of cheeses happening with CIP scheduled between 6 a.m. and 10 a.m. And then our whey operations are about a 3-hour lag behind that. And that's really a function of how long it takes the cheese making process to go from starting the milk process to being into whey processing. The cheese making process, as far as the liquid side, tends to be about 2 or 3 hours long, sometimes a little longer for different cheeses. But that lag tends to be a fairly consistent thing in cheese manufacturing between the CIP schedule of the cheese plant and the whey plant. So when we look at what's going on with that, what are the impacts of that? Water consumption is typically much higher during the CIP sequences in a plant than they are in the regular straight running time. There are certain CIP processes that happen all the time, such as trucks or washing cheese vats between individual vat batches. But generally, the bulk of the water consumption, at least as far as CIP goes, happens during those CIP windows. If we're going to recover polished water from our whey processes, that polished water is generally going to be produced at a consistent rate along with the operation of our whey plant. So this chart has water consumption in red and water production on that bottom, second to bottom row in black and green. And then from there, we just do a running total of how much water we are accumulating or decumulating as we start to consume it for CIP. And then the little chart above gives a pretty good representation of how much polished water do we have on hand in this theoretical process. And you can see at the beginning of the day or at the end of CIP, we're starting off with nothing, but we need to be able to store over 120,000 gallons of water in this model in order to not have to throw water away because we don't have any place to park it, just to accommodate that surge through the day. Go ahead, Grace. So let's talk a little bit about considerations for storage and distribution of water. Storage vessels need to be cleanable. They need to be large enough to accommodate all of the water that's going to be produced. You don't want to have to throw water away. Certainly there's practical limits on that. And one of the things that's pretty handy is, depending on how big a system you have, if you can have multiple tanks, that lends itself to being able to flip those tanks to be able to clean them or cycle through them. It also can lend itself to being able to operate those tanks at different temperatures, which lends itself to energy recovery from hot or cold water streams to other processes in the plant that you might want to be able to recover water from. Quality of that reclaimed water is primarily a function of how it is produced, but how we store it and handle the distribution system is a key part of that as well. UV disinfection is pretty common in plants nowadays for water coming off of RO polishers. Chemical treatment is also acceptable, and there are benefits and drawbacks to both. UV is pretty effective at sterilizing the water that passes through it, but the nutrients in that water remain. And so if you have other things happening downstream, you're not sterile, certainly. There's the possibility that something is going to grow from those nutrients in that water downstream. Chemical treatment can provide a more persistent disinfection function, but depending on the chemicals, they can be pretty costly and or they can potentially be corrosive on equipment, particularly if they wind up getting over concentrated. So those are a couple of different considerations that go into quality of that water production. Distribution systems for reclaimed water should be capable of, not quite yet there. Distribution systems for reclaimed water should be capable of distributing water at capacity and pressure necessary to the different things that they're feeding. You don't want to have a situation where your UF system's trying to get 300 gallons of water, but your reclaim system can only deliver 200, and now you're slowing down your production processes. Pretty much anytime you have a distribution system delivering polished or reclaimed water, you want to be in a situation where you have redundant water behind that from a more traditional potable source, so that if you do have a production disruption in your polished water or your water recovery, that you don't find yourself trapped. You don't have a dirty piece of equipment that you need cleaned in order to make polished water, but you need polished water to clean that system. That's a trap you don't want to get caught in. With regard to distribution systems, we very much suggest that they be designed for at least some degree of clean in place in order to be used effectively and cycled properly. It doesn't have to be an automatic push a button CIP the distribution system kind of a thing, but you definitely would like to have it plumbed in a way where it's not difficult with a couple of swings or jumpers or even a couple of hoses to be able to circulate cleaning solution through the entirety of the distribution system. If you ever have an upset or you ever have a problem, if you go the extra mile as you design a system and lay a plant out, the ability to get that system back online with high confidence that you don't have a lingering problem is really pretty valuable. A clean break in any risk is really handy to try and get back online, as opposed to not really knowing whether or not you've got your full system clean. We definitely suggest designing things to be at least CIP-able with swings. And if you want to go fully automatic, that's not a terrible way to be either. A well-designed system is capable of CIPing within the production sequences of a regular plant to the point that you can CIP your water distribution and storage as regularly as you do your milk silos and milk pasteurizer. There certainly is cost associated with that, but it's something to consider, particularly depending on scale and how much water you're talking about. Okay, go ahead, Grace. So this is a little diagram, fairly simple, of what I've kind of been referring to a little bit. So we've got a polisher that might be delivering polished water to a cold storage silo, and there might be some cold water distribution off of that. That cold distribution might be useful to go to diet filtration or something like that. But one thing that we can do with that water, in addition, is we can use it for some heat recovery and kind of get some value out of both the energy recovery ability of that water, as well as then ultimately the water itself. So this diagram, as we go down from the cold storage water silo, is presuming to get recovered against whey coming off a pasteurizer. And then we could supplementally heat that if we wanted to and get it to whatever final temperature we think is useful for the plant. I've got an example here of 120 degrees Fahrenheit. 120 degrees Fahrenheit is a handy temperature to have hot polished water at, because it's really the ideal CIP temperature for the membrane systems that produce this and any other membrane systems that might be in the plant. And by rinsing those systems and delivering 120 degree water to them, we save any heat up time it takes for those to operate, so that we're able to cycle the plant faster. Membrane cleaning is one of the slower CIP operations in most dairy plants. And if we can do the processes at the right temperature right out of the gate, we can save 10, 20, 30, 40, 50 minutes of CIP turnaround time on a membrane plant. And that's usually pretty valuable time. The water that's recovered then off of a heat recovery process like this can go to any number of sources. And again, ideally, we design that distribution system to have enough destinations to use up all of the water that's produced over the course of a day. Go ahead, Grace. This slide is a little bit less specific about water use, and it's specifically just talking about energy savings through regeneration. This is something a lot of people in the dairy industry are doing already, but it's worth highlighting because it's pretty high value. What I've depicted here is I've depicted raw milk running through a preheater and then a regenerator and the primary pasteurizer heater, with heat recovery between that milk preheater and a whey heat recovery section. So a whey pasteurizer or a whey heat treat system might have whey coming back through its own internal regenerator, then getting subsequently cooled further before it goes to a final cooler that's going to take it down to a temperature where membrane systems might start to fractionate, which might be a 60 degree temperature. And so the addition of this loop between raw milk preheat and whey HTST heat recovery is saving approximately 3,600 pounds an hour of steam on the milk pasteurizer and saving about 275 tons of refrigeration on our cooling requirements for our whey pasteurizer. And that's $400,000 roughly in energy savings on an annual basis. That's pretty good payback for putting in a system like this if the capacities are similar to what this model is. One of the reasons I wanted to throw this in is because it carries on to the next slide, if you would please, Grace. And this would be the same design, only now incorporating what I was referring to before, and that is the use of polished water that's cold, coming off of a cold membrane process, being used as another heat recovery section. So now our whey coming off a final heater and going through an internal regenerator is first passing over cold polished water. And that whey is being cooled down a first step, while that polished water is being warmed up closer to target CIP temperature. Subsequently, we're still able to get good heat recovery between the whey and our milk pasteurizer because we still have good differential temperatures between all our sections. And now, under regular operating conditions with both of these heat recovery functions operating, we no longer have any need for our final glycol cooler or chilled water cooler to provide any energy input or removal to get our whey down to membrane processing temperatures. Now, one trick with this particular design that people deal with or struggle with, this looks great until my milk pasteurizer goes down, because my milk pasteurizer goes down 3 hours ahead of my whey pasteurizer. So now what do we do? Well, if you don't have this secondary heat recovery function available, what you do is turn on a couple of compressors in your refrigeration plant and put out a whole lot of cooling in order to get your way down to target temperature while it's operating. If you have this design, and if you've been accumulating a little bit of cold polished water all day in anticipation, now you can turn the flow rate of your cold polished water up, and you can draw most of that heat into your cold polished water and vastly reduce the peak that hits your refrigeration plant. And a good approximation for this example is that we're about 400 tons of refrigeration savings using heat recovery here as if it weren't there relative to just doing all of the cooling off a straight refrigeration system. And 400 tons of cooling over the course of time, just for the hours a day that it's actually in operation, is still good for a couple $100,000 a year in savings, plus the capital cost of potentially not having another 400 tons of refrigeration capacity in your facility. So definitely some value there when you start talking about bigger facilities and bigger volumes. Go ahead, Grace. So let's talk about economic considerations a little bit. There are some substantial capital costs associated with water reclaim, storage, and distribution, and they don't necessarily scale linearly with capacity. Those costs do vary substantially by region. What might be, barely good payback in Wisconsin or Minnesota might be fantastic payback in California and Arizona. And there are definitely some operational requirements and complications that come with having a system like this. Managing water inventory is not push button easy. It takes a little attention. It takes careful planning. Anytime plants have upsets or changes in operation, those impact all of those water volumes. And so you want contingencies and good understanding of how that system works to be able to manage it. One of the plus sides is if you're renovating processes in plants, frequently the equipment that might be left over from that could be suitable for handling water. So sometimes plants that are making changes are able to leverage existing silos and things like that for some of these storage functions. And assuming we're not crowding too bad here, I just have a couple other little low-hanging fruit items. Rinse recovery tanks on CIP systems are probably the most economical investment for water reuse in a plant. It's always worth keeping an eye on your CIP systems. Are we flushing longer than we need to flush? We can save a lot of water if we just keep an eye on that. And automation can definitely help people to minimize the amount of excess water used. Turbidity sensors can optimize product recovery and minimize water use at the same time. Those are some of the high value things that we look for when we're helping people in their plants. Beyond that, not too much else. Obviously, a few points maybe on water quality in general. Reliable maintenance, chlorination, and filtration and cleaning, regeneration of equipment helps ensure reliable operation. Pretty much goes without saying. Operating systems beyond their design capacity or beyond their cycle life, particularly like for membranes, those are a couple of things that negatively impact water quality. And managing those types of things is definitely one of the key requirements to getting things to operate. That's about all I've got. I'll pass the baton back. Thanks, guys. John?
All right, thanks, Aaron. Particularly interesting there on that water reuse in the heating and cooling. I appreciate that. All right, we're on to Rachel. Great talks, and we'll get to Rachel Kloos from ISG and water recovery from dairy processing wastewater. Take it away.
And fantastic. Thanks for having me, guys. I'm just super jazzed. We've learned so much over the last half hour and really getting excited and energized about going out and looking at all those low-hanging fruits and things like that. So I'm going to continue the trend that Scott and Aaron has put forward. I will not have an example of recovering urine from Japan or from the space station. So if anyone's going to be disappointed to that, make your comments in the comment section. That's fantastic. So moving on, next slide, Grace, please. I'm from ISG. We're a full discipline engineering firm. We tackle everything. And I really like to talk a little bit here before we jump on is about looking at the holistic process. Scott and Aaron talked about how heat recovery and how your CIP system and everything like that is going to be further related to how your water system and how your wastewater system works. So holistically viewing that whole component. Next slide, please, Grace. And just on that, my name is Rachel Kloos. I'm a water wastewater group leader here with ISG. I'm dedicated to industrial water and wastewater solutions. I really like to focus on possessed, maybe obsessed, maybe is a better word, on sustainability and robust solutions. It's so cool to watch our process, watch our industry continuously get better, and find the things that we thought were maybe abnormal or very unique, like some of the stuff that Aaron was talking about with some of the heat recovery, are going to be normal things that we're going to be doing 10 years from now, 5 years from now. So pretty exciting as we move on. Next slide, Grace. All right, I'm going to start out with is that we understand that water is essential to your business. We also know that dairy processing uses a lot of water. And then if you add in the coupled with the adjacent water demands of the dairies producing the milk, the industry is under a lot of scrutiny, and it's going to continue to happen. So no matter where you're at, if you're in a water scarce environment or area, or if you're in a water area that's got a lot of water, you're still going to be under scrutiny for water use. So it's our responsibility to make sure that we are efficient as possible and continue to drive those efficiencies. I want you to sit back and imagine a day without water and what your plant would do. Aaron talked a little bit about having a plant that could run and recycle as much water from the milk, from the cow water and the polished water to continue to move those systems forward. Could you do that right now? How do we do that? And what would impact would that have on your business if all of a sudden your supply of fresh water was limited, was restricted? And I know all of you out there have maybe had some of those instances happen. We're starting to see them a lot more, in which maybe it's a peak demand that we're limiting, maybe it's a daily gallons per day, but water scarcity is becoming a bigger issue. So what's going to happen is this relative to the amount of storage that you have on site. Can you get by to reflush your equipment? Does this impact your firefighting capabilities? Can you flush a toilet, which is really important? All those different things, making sure that we recognize that water is an essential ingredient in our process. Next slide, Grace. So let's talk a little bit about this. I'm going to use a little bit of buzzwords coming through here, but the concept of water positivity, this is out in the industry right now. This is what everybody's talking about. The concept of water positivity involves enhancing the regeneration of water resources beyond the amount consumed, meaning we're going to put more water into the environment to replenish the water supply than we're taking out to make our product. And what better way to think about that is in the dairy industry, when our raw ingredient milk is predominantly water, and we're able to recycle that. So by integrating practices like water efficiency, increasing water recycling, and advancing sustainable water management practices, we can then move forward. Little example on here, Amazon Web Services, big data center operations all over the world. They are committed to being water positive by 2030. What does that mean? That means that they want to put more water out into the watershed, into the environment, than they're using to cool their data centers. And they're doing this by a combination of efficiency, new technology, doing creative things, and then also integrating recycled water into their system. Coca-Cola, for example, different concept is that we can now look at the reduction of water, and they're committed to constantly impacting the amount of fresh water that they're using on their product. And they've committed by a reduction of 2025 from 2019 of water use. Next slide. So let's kind of maybe go in there on the Coca-Cola example, because I want to use this as an analogy as we jump into the dairy and then specifically getting into wastewater, is how do we go about this? We look at that low-hanging fruit. We've kind of talked about that a couple times already. Is in 2020, they were at 3 gallons per gallon of Coca-Cola. So now all of a sudden we're looking at the stuff that's laying on the ground, the fruit on the ground. This is the easy stuff. This is the leaks that you can physically see. These are all the things that are very integrated that we can find. And then as we move up that chart, it's going to get harder. The low-hanging fruit, we're able to jump down. In 2024, they announced they were at 1.79 gallons of water to produce a gallon of Coca-Cola. Has anyone ever drank a gallon of Coca-Cola? That does not sound like fun. But in moving on, and their goal again to get down to 1 gallon per gallon of Coca-Cola by 2030. So kind of using that same analogy that we're going to go after as we look at it into the dairy processing industry. Next slide, Grace. So let's apply this same logic, the apple tree of fruit, if you will, to our industry. Step one is efficiency and creating that metric. So Scott and Aaron both talked about that. If you don't know how much water you're using in your plant right now, you need to figure that out. You need to look at that metric. You need to compare that metric to others. Make sure, compare it to yourself, trend that over time. This may include getting additional metering or getting additional data collection. But we have to understand where that fresh water is coming from. And the reason we're doing this is so that we can better understand how that's going to impact the rest of our system and how do we get better. If we don't know where we're at right now, we can never get better. And Aaron talked a little bit about the mass balance and water balance. This is a key component as we go through here. You make sure that you're doing a water balance on your system so that you understand everything from tracking your fresh water coming in and relative to the milk, the water component in the milk, but also subtracting your water losses, your water to your atmosphere, your product, and going to wastewater, for example. How can we track improvements if we don't have that data? Next slide. So here's just a really quick example of doing that water balance. Again, roughly a 4 million pounds per day milk plant, kind of moving in that direction. This is an arbitrary example we took and subtracted. And what we found is that there was we are unaccounted for water of about 64,000 pounds per day. This allows us to actually have a goal to go after and track this, make sure that we understand that. We can start searching for unaccounted water. Remember to optimize where our fresh water is using, and we're picking the fruit off the ground. Remember, that's where we're going. In this example, we found a line feeding water to a fill station leaking underground. So again, it wasn't going to wastewater, it was going out into the atmosphere, moving in this direction. But without looking at these numbers relative, it's really hard to quantify. And then, first of all, this could celebrate your successes as well. Next slide. All right, second step. Now that we've looked at efficiency and we've got our metrics in place, it's time to start working on things. And that's a lot where Aaron and Scott have talked about utilization and optimization of cow and polish water. And you're thinking, what does this have to do with wastewater? Well, it has a huge essential. As you guys are well aware, wastewater receives everything that you guys produce. So we have to deal with all the ups and downs that are happening. And cow and polish water are replacing fresh water. So here's an example, incoming water stressing the supply. Again, we've got a community that maybe is a little stressful about the amount of water that we're pulling in the mornings, but then also noted that we've got excess polish water. And just like Scott and Aaron talked about, we have excess polish water at the wrong time, maybe not when we're cleaning, but we don't have that excess polish water when we need it. So we're having to supplement that with fresh water. That excess polish water was a result of a few things, not enough storage potentially, but in this particular example, it was providing a lot of benefit to the wastewater plant. I'm not going to say it out loud, but if you kind of think about, Aaron talked about polish water being somewhat cold or colder. Wastewater is usually in that warmer side. So a lot of times polish water and cow water is used to help cool things going out to wastewater. And it does have a beneficial effect as far as temperature, but it is requiring a lot of hydraulic loads that's coming in here. So if we just kind of look back here and say, hey, by recycling and making sure that we're optimizing some of that polish water in the plant, we probably will never get to zero, but getting very close to that, we were actually able to reduce our wastewater load significantly. So again, which is everyone's goal, is to help make sure that wastewater is just running efficiently and everything. So that's, again, an example of where optimization, understanding where your water use is, making sure that your timing, your water balance timing, like Aaron mentioned, is really optimized, and how that's going to impact wastewater as we go through. Next slide, please. So number 3, as we kind of get to this part of the system where we feel like we've optimized all our efficiency, we've really optimized our cow and polish water utilization, this is where we're getting up to the top of the tree. It's going to get harder and harder, but this is where we kind of talk about reuse. The reduction in water becomes a lot more difficult here in this case, and we're not going to sugarcoat and say that water reuse is an easy answer. We talked about being able to CIP this, being able to manage organic growth and disinfection and chemical additions. All those things come into place, but it is possible. Once we've exhausted all the efficiency and internal reuse, we can now start talking about the treatment and use of treated wastewater. So before we jump on, we want to also look at this as wastewater is a resource at this place. We're changing the dynamics, and how we talk about wastewater is becoming a potential resource to be able to mine or extract that water out of that. The other thing that we want to think about is when we're looking at this, domestic sanitary wastewater, which is coming from your kitchens, your bathrooms, it's not acceptable. We don't want to use that for reuse. So making sure that your system has that separated so it's not going to your industrial wastewater plant. And then looking for applications now that reuse may be an option. So this is where we brainstorm a little bit and start looking about traditionally looking for those non-contact situations where we're not contacting any product, we're not contacting any place where potable water is required, but we have those options to look at. And before we jump into that, we're also going to talk about water quality. So as we start brainstorming of those areas, and we're going to talk about a couple examples here in just a second, but water quality becomes your limiting factor as we move forward. Next slide, please. So finally, it's time to start looking at wastewater as a resource. How do we get started here? So let's look at it on a regulatory standpoint. Can we look at reuse of some of our treated effluent wastewater on a regulatory standpoint? Can we utilize that? And that's, again, it's going to be related to your PMO, which Scott talked about extensively in the very first part of this section, and reuse standards specific to the state. Traditionally, when you're doing internal reuse in your facility and you're not contacting any food product, and you're not using it for potable water services where you may impact a human health component, there's a lot of flexibility in how we can analyze and look at those applications. Now, there's lots of things that we need to do, but that's the first analysis that we look at specifically, is looking at that regulatory component. Can we use this water, and is it applicable that's coming in? The second thing that we're going to look at is the quality of the water. Once we determine, yes, we can physically do it, not all water is created equal, right? We're going to look at the quality of the water. And then we're going to ask ourselves, should we reuse it? Is it a component that is it an efficiency addition that we want to use? Is there a risk factor that comes into place that comes in? I have a great example when we were reusing water out of a warm cooling tower pond and reusing in the cooling tower. And in that case, we had a lot of geese that would land on those ponds. And as you can imagine, all that geese remnants would come into that water. And it became a very big risk factor to manage in your evaporative cooling recirculation. So managing those risk factors and then applying hurdles to make sure that you've got the proper safety factors in part of that. And then the other one is that not all wastewater, treated wastewater for reuse, may be applicable to your application. It may be that your neighbor could use it, right? Maybe there's a metal finisher facility right next door, or maybe there's some irrigation that can happen. So, but all of those things can happen as we go through. So that's the very first thing, is we look at it as a resource, and then we look at opportunities for those components. This is an example here of recycled water going into an open cooling tower. And you can see a little bit of foam coming in on the inside. It's something you got to manage, right? Even recycled water in its component is still going to have those opportunities. So just looking at those risk factors. Next slide, please. Finally, as we get into water quality and kind of start to close all this up, is we want to look at specifics. And a lot of people think, hey, if I throw my wastewater through a couple more filters, everything's going to be perfectly fine. And a few things were looked at specifically. So we talked about, hey, let's brainstorm on some of the applications that we could have. And then second, let's go back and look and see what the impact of the water quality is. The first one that I want to bring up is temperature. Most of the time, the effluent is on the warmer side, so it does limit the capability. One of the most common places that we start looking at for opportunity for reuse of treated effluent is in cooling towers. If your water's already warm, that's not going to help you much with cooling, right? So we have to be really careful about managing that and understanding what the cooling limitations are of that water. The next one is total dissolved solids, and we've all talked about that. Cheese manufacturers will traditionally have a higher total dissolved solids in their effluent, and traditional biological treatment doesn't remove total dissolved solids. So this is going to be a limiting factor, specifically if you're using it in utility applications in which you're going to be cycling up that water. There may be limitations where you're using now more water because you're having to discharge that water in order to not cycle that water up as much as possible. Hardness is another one. Scott and Aaron both talked about scaling tendencies on evaporators, on piping equipment, etc. We want to make sure that the hardness component, that scaling tendency of that water, is not going to cause more issues. I had a recycling opportunity at one time where the scaling tendency of this water was on the higher side. And as a result of that, a lot of the recycled water piping that we were using for distribution became scaled up. So we had to spend extra time and energy cleaning up and descaling those pipes, which actually created a lot more trouble and a lot more havoc for managing that recycled water system. So in hindsight, kind of going back, we adjusted the scaling tendency of that water and we were able to eliminate those practices. Chlorides is another one. Chloride content specifically on stainless steel applications or things can be problematic. So, and these are not usually easy things to remove for tertiary treatment. So kind of watching those things. And then finally, suspended solids and then your BOD and organic loading are going to be a big factor. Just like we talked about the example going into the cooling tower, we want to make sure that that cooling tower stays pristine and clean. We don't want to give a lot of organic loading into that system. So making sure that the water quality of whatever effluent we're going to be utilizing does meet the specifications for that reuse application. And it may apply to adding additional tertiary treatment on the backside to meet those water quality requirements. Next slide, please. So as we look at the concept of water positivity involving enhancing the regeneration of water resources, we can apply that same apple tree concept here. So we start with that cow and polished water utilization, making sure, and again, you said, hey, we're supposed to be talking about wastewater. Well, you guys optimize that stuff. Wastewater is going to be much happier on that end. So cow and polished water optimization and utilization is going to minimize that. There was a little comment as well, thinking about specific incoming water quality. Cow and polished water quality is usually traditionally a lot better than your incoming water. So it does reduce the amount of pretreatment that has to happen on your incoming water, which would ultimately reduce the amount of wastewater that's happening there as well. The second tier of that, this is that low-hanging fruit, is looking at those efficiencies, doing those water balance components and looking at what that impact is. And then finally looking at those reuse applications and thinking about the very strict regulations that we're looking at, right? Whether it's phosphorus, chlorides, total dissolved solids that are coming up and creeping up into our regulations, but also looking at how water reuse can help impact those and where that resource can happen. Next slide, please. So finally, water is an essential ingredient that is often overlooked and assumed that we will always be there. It's pretty cool to hear all the stories and see. I'm excited to see this industry work hard together to share best practices, optimize, and improve the water footprint of our favorite products. So please share some of your stories on where you're at, benchmarking, things like that. We would love to hear a little bit more where you're at and see what optimization, because we definitely want to move the industry forward in that water footprint, right? Going water positive. That's all I have. Thank you, guys.
Right. Thank you, Rachel. We'll wrap things up on time, but I will let you know that we had some questions come in advance. And thank you to Scott answering Joel's question on the chat. The ones we got in advance, we'll throw to our speakers and we'll try to get those to you after the fact. But we don't have time to address them now. So we appreciate the great presentations from our speakers. And I think I'll throw it back to Grace because we always try to end on the right minute.
Yes, we will. Thank you, John. Thank you all for joining us again today. We appreciate you joining us for this fascinating topic. I also want to thank our sponsors, again, Nelson Jameson and Applied Science, for their generous support. And thank you again to our presenters, Scott, Aaron, Rachel, Dean, talking about the new CDR course. We appreciate all of you giving your time and expertise to WCMA members today. One last quick plug, our August WCMA webinar will focus on food safety. Presenters and topics are soon to be announced, but you can register for that now on our website. We'll also send out the link in our follow-up email. With that, we'll send you off right at 2 o'clock. Have a wonderful afternoon, and thank you so much for joining.